Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This lecture 3 is the introduction of the metric tensor. The metric tensor is a solution of a gravitational problem. It tells us how a space is curved. Now we want to look at the relation between a co- and contravariant basis in a curved vector space. As we made the transition from a flat to a curved space, we avoided to use upper indices. We had this equation, and the left basis is written as primed vectors, but now we can identify the left vector basis as the contravariant basis. So we have this, and now here we have two matrices, n transpose n. The result is a new matrix. We call the matrix now G, ij here. And of course we must write it as a contravariant matrix because we must execute the multiplication in the right way, and there is summation of components. So here J is the counting index. There is sum over the J index. Okay. Then we can write down the two matrices n transposed n here. And if we look at the left matrix, we can say we have three column vectors. If you look at the first column, okay, there is always x1, but we count in the y index from 1 to 3. And so we can write here three vectors with a counting index I here. In the right matrix, we can say we have three row vectors. If we look at the first row, there is x1 in the denominator, and we count again for y, for the components for y, from 1 to 3. So we can write here three vectors like this. So, okay, all we can write for the left vector, G vector with index I, and here for the column vector, G vector with index J. Or if we want to write down explicitly the result of the multiplication, then we have these differential quotients. Okay. The scalar multiplication is commutative, and that means that there is a symmetry in the indices. That means the matrix Gij is equal to Gji. That means also that we have now 9 independent components in the matrix, but only 6, or in the 4-dimensional space, instead of 16 independent components, we would have only 10. And here we have contravariant indices. Now we consider the covariant indices, the covariant G tensor or matrix. To calculate the covariant vector, we multiply 71 here with the inverse matrices, means n transposed inverse and n inverse. So we get this equation here. And we had the relation between the n and m matrix. We had n multiplied by m transpose is the unit matrix. And so that means we can write, instead of these inverse matrices, the m matrix here, m transposed m. Or, again, we write for this matrix product G matrix, but now here covariant Gij. Okay, let's analogous to the contravariant version of the G matrix. And now we want to know what is the inverse of the contravariant G matrix. Okay, we have for G, the product n transpose n. And now to calculate the inverted matrix, we have to take the inverse of both matrices and have to exchange the order of multiplication here. So that means here we would get n inverse multiplied by n transposed inverse. And that is exactly what we have here. And so this means obviously that the covariant G matrix is the inverse of the contravariant one. So we can write this. The inverse of the contravariant matrix G is the covariant matrix G, or vice versa. And that also means if we multiply both matrices, then we would get the unit matrix. Okay, here we must be careful with the writing. If we do it like we have written it here, so we wouldn't get a matrix, that would be a scalar. So we must write for the element in the ith row and jth column, this, the counting index, that's k. Then we would get a delta Kronecker because we have as a result the unit matrix. In analogy, we can also write explicitly this 79. And of course, here we have got the same symmetry in the two indices. That means Gij is the same like Gji. And there is a third possibility. We can have one co and one contravariant index for the G matrix. Okay, we can easily calculate that now. Easily. The mixed co-contravariant matrix, that is again the product of the two G vectors. And for the covariant G vector here, we can write this. And now the matrix multiplication is associative. That means I can write the parentheses in each position. It makes no difference in the result. So we write the parentheses now around the two G vectors here. And this again gives a G matrix. And here we see, that's again the Kronecker delta, the unit matrix. So that means, the mixed tensor here, that is the unit matrix. And now we compare an arbitrary co- and contravariant vector. We can write for an arbitrary vector v. We can use the covariant components or the contravariant components here if we use the right vector basis here. Okay, we solve it first for the covariant vector v. And so we multiply with J covariant from the right. So we would get this here, 83. And we know this product here, that's the Kronecker delta. And if we multiply with the Kronecker delta here, nothing would happen. The only effect is, instead of I, we have the index j here for the v vector, covariant v vector. And on the right side, we have this product of the contravariant vector components with a covariant G matrix. or for the contravariant vector, we have this. Yeah. Okay. And yeah, now the G matrix is called the metric tensor. Yeah, we have only talked about the matrix here. We can say every tensor is a matrix. That is right. But not every matrix is a tensor. That is wrong. The components of a tensor are always related to space coordinates. We can use the metric tensor to exchange the covariant coordinates of a vector by the contravariant ones, and vice versa. Now we want to consider an example. We want to know the shape of the metric tensor in spherical coordinates. Okay, be careful. Spherical coordinates are curvilinear coordinates, but that does not mean that the space is curved. No, the space is flat here. We use, like in classical mechanics, spherical coordinates in a flat Euclidean space. Okay. If we want to calculate the gradient again, we must define the new unit vectors for the spherical coordinates. We had such a formula here in 20 in the first lecture. Okay. We must differentiate the position vector with respect to the new coordinates r, theta, phi. Okay, and we must divide by the absolute value because we want to have unit vectors again as basis vectors. So we have here written the same but with absolute value bars. And okay, we can write for the absolute value h Hertz. Okay, so the position vector is here given by this. That should be clear from the basic lectures. If we want to know the Cartesian coordinates by using the spherical coordinates, then we would have for the x coordinate r sine theta cosine phi and so on here. So these are x, y and z. And then we begin with the first coordinate r, er, the base vector. Then we differentiate with respect to r. That means, yeah, here in the position vector, yeah, okay, r is cancelling out here. So, and in the denominator, we need the absolute value. So we have to square the components, add them, and write a square root over them. That is a three-dimensional Pythagorean theorem here. Okay, then we have sine square theta cosine square phi here in the first coordinate, and here is the second and the third with a square. So in the first two idents we can factor out a sine square theta. That means we have cosine square phi and sine square phi. That is 1. So, and then sine square theta and cosine square theta is 1. And the square root of 1 is 1. So we have only 1 here in the denominator. That means the ER vector here is given by this expression here, 89. Okay. Then we continue with the second coordinate, theta, e theta. We differentiate with respect to theta. It means here we have sine theta, differentiated means cosine here. Here again another cosine, and the cosine differentiate, that's minus sine theta here. Then again in the denominator we have the squares of the components and the sum of them, and then write over them a square root. And here r is cancelling out because r squared, taking the square root is only r, and so r in the numerator, r in the denominator is cancelling. Then in the denominator we have the same with the trigonometric functions. We can factor out cosine square theta in the first two addends. That means we have cosine square phi and sine square phi. Means this is 1. And then cosine square theta plus sine square theta is 1. That means there is only a factor 1 here in the denominator. And so what we have here in the numerator without r is that what we have as a result here in 90 for e theta. Then the last one, e phi, we differentiate with respect to phi. And so that means again here we have cosine phi, and the position vector means sine phi and minus. And then we have sine phi, so that becomes a cosine phi here. And in the third coordinate is not dependent on phi, so it vanishes. It is 0 here. Then in the denominator we have the squares again of the components. R is cancelling out again. So here sine square theta can be factored out. And so sine square phi plus cosine square phi is 1. And then the square root of sine square is only one sine factor, sine theta. And so we can cancel out another sine factor in the numerator. So we have only minus sine phi and cosine phi and 0 as the components of the unit vector e phi here, 91. Then we can write for the gradient, that should be clear from classical mechanics, but we do it again here, the derivation of that. The gradient of function phi is then, we have the differential quotient and the unit vectors, and we have in front here a factor, perhaps hi. That's the absolute value of the calculation here. Then, in the first component r, er, there was no factor. We had only 1 here in the denominator, so here is no here's a factor 1, or no factor here in the first coordinate. In the second coordinate, theta, we had here a factor r, and the other things here under the square root became only a factor of 1. And so here only r, 1 divided by r, as a factor at the second coordinate theta here. Then in the third coordinate we had a factor of r and sine theta here in the denominator. And so that's what we have to write here into the equation for the gradient. So we have here r sine theta as a factor at the third, the phi component. Okay, and now we want to define the g vector because by defining the G vector, we can then calculate the metric tensor, like we had done that before in the last paragraph. And we have first for the vectors gi, this expression, the differential quotient with respect to the coordinates multiplied by the unit vector in the 3 dimensions. And then we obtain here these 3 equations. We must recognize that these 3 components here in these vectors are the expressions for the Cartesian coordinates. This is x, this is y, this is z. So we write here the 3 components with ex, ey, ez. And okay, in the first line, this is the r coordinate, then the theta coordinate, and for the phi coordinate we have here the third line. And these are the vectors we have determined here before. And then if we want to calculate the metric tensor, here the covariant metric tensor, then we have obviously multiply a G vector by itself. Then we would get this result here. This is an exercise for students. Do that calculation explicitly and show that all these trigonometric functions were vanishing. Okay, only the sine square here is here in the metric tensor in the last coordinate. That's the only trigonometric function which isn't vanishing. Okay, and then we get this metric tensor 97. This is a covariant metric tensor in a flat space in spherical coordinates. And then for the contravariant tensor, that must be that the scalar product of the 2 metric tensors here, co and contravariant, is the unit matrix. So because you have only a diagonal tensor here, that means the inverse. For the inverse we have also diagonal tensor, but with the reciprocal values here. We have here 1 divided by r square and so on. Okay, then we can then calculate the contravariant vectors G. So very easy now, because we can, instead of writing a contravariant vector, we can write a covariant vector with a scalar product with a metric tensor here in this way here. So first coordinate r, gr, that is gr, and here scalar product. So that is the same like the covariant component, because we have here only one, there is no factor. But if we consider the theta component here, then we get the additional factor 1 divided by r squared here, and the same for the third component phi here. We have this expression, and we find here of course the factors which we have here in the metric tensor. Okay. Now we want to look at the metric tensor in several coordinate systems. We have seen that the metric tensor in the flat space in spherical coordinates is a diagonal one, and the non-diagonal elements are 0, But in general, we must write down all the elements. Here in the two-dimensional space, we have for the line element here in 102 this expression. We have the metric tensor Gij and the two vectors xi, xj. This is a double scalar product. And yeah, we would have normally 4 addends here, but we have only 3 because of the symmetry of the metric tensor. The G21 element is the same like the G12 element, and so yeah, here we have twice this element dx dy. And in the three-dimensional space, we don't have 9 independent components, we have only 6. Because, yeah, 3 are double because of the symmetry. So dx dy is double, dx dz is double, and so on. In the special case of the flat space, of course, and Cartesian coordinates, we have for the metric tensor, yeah, the unit matrix. In the two-dimensional space here, Gij is 1, 1 in the diagonal, or three-dimensional, 1, 1, 1, 104 here. But we know from the special theory of relativity that we live in a so-called pseudo-Euclidean space, or also called Minkowski space. And yeah, that means that the time coordinate has got another sign than the space coordinates. And yeah, the normal convention is that the time coordinate is taken positive and the space coordinates are taken negative. And yeah, here if we look at 105, this metric tensor in the four-dimensional flat space. And the first coordinate, that's the time. And we count here from 0 to 3 in the coordinates. So that means the 0th coordinate is a time. Yeah, and then the first coordinate, that is r or x, and the second, that is y or theta, yeah, and so on. Yeah, here we have Cartesian coordinates, and so because of the pseudo-Euclidean space, we take here the space coordinates as negative. So 1, -1, -1, -1. And yeah, if we work here in the four-dimensional space, we use now Greek indices, like here g, mu, nu. In polar or spherical coordinates, we would have the following metric tensors. In the two-dimensional space here, we have 1 and r squared. Three-dimensional space, that what we have derived before, that is 1 r squared sine squared theta. And now in the four-dimensional flat space in spherical coordinates, we would have this here. The time coordinate, the first one here, is positive. And now, yeah, the 3 space coordinates, the space components, which we have here in the three-dimensional space as positive, now are negative. Okay. And yeah, in 102 we have seen here in the general expression that there are some mixtures of the differentials dx dy and so on. And to show that we have not always diagonal elements, then we look at an example. We want to rotate want to make a rotation in the xy plane, we say we have the angular velocity omega. And then for the Minkowskian line element, we would have ds squared. And here, this is a 4-dimensional Pythagorean theorem, but using the pseudo-Euclidean geometry. And so the space coordinates, the squares of the differentials in the space coordinates are negative. Then we want to know the new components of the transformed coordinate system. So we write ds primed here, and we have only a change in the x and y coordinates. So here we have only x and y as primed as new coordinates. There is no change in z, and there is no change in the time coordinate. Then that should be known from the basic lectures in theoretical physics or linear algebra. If we want to write down mathematically rotation, then we do that by using the cosine and sine function, like here, 109, 110. Z remains the same. And if we have angular velocity omega, then we must write in the arguments omega multiplied by the time to get an angle. Okay, and now we need for the line element above here the squares of the differentials in x and y. So we differentiate here dx primed with respect to the time t. So here we have a product of two functions. So that means we would get two addends here in the differentiated formula. Now, we have differentiated x, that's here. And the cosine function remains here as a constant, we could say. And then in the second term, x remains unchanged. And the derivative of the cosine function is minus sine. Here minus and sine. And we have an inner function, omega t. That means we must apply the chain rule for the differentiation. And the inner derivative, that is omega. And so we get here an additional omega factor. And we do the same now for the second addend here in 109. So we have two further addends here in 112. And now we need dx, so we multiply by the differential dt. So then we have here 113. Okay, and we need the square of the differential. So here this is dx primed squared in 114. We have here 4 addends and squared, so we get here many addends. And we do the same for the differential dy or dy squared, primed squared. And now we substitute them in 108 here, the primed dx dy. And this is an exercise for students. Yes, calculate the other differential dy, take the square, and substitute, and then many of the addends here will cancel out because we have same terms with positive and negative sign and so on. Much is cancelled out then. And what we get is here 115. And yes, indeed, we see now here in this new line element, we have some combinations in the differentials dx dt, dy dt here. Okay. And so we must write in general for the general line element in any space, ds squared is equal to g mu mu x mu x mu here as a double scalar product in the two indices. And what we can say is that for spherical symmetric problems, we have always a diagonal metric. If not, it must be possible to transform the metric into a diagonal one. Okay. And now, we want to look at some formulas which the students can find in some textbooks. And they see the formulas and they don't understand them. So we will especially look here at the so-called cofactor. The first equation is here 117. So we have here G mu nu, the metric tensor contravariant, is equal as the cofactor with the indices mu and nu divided by g. G without indices means the determinant of the metric tensor, of the covariant metric tensor here. That's very important. And delta is the so-called cofactor. It is a subdeterminant. And that means we have the covariant metric tensor and we have to cancel the nth row and the nth column. Okay, then we look at an example. We make a calculation with the indices 2 and 2. Mu is 2 and nu is 2 as well. And so we set in here in 117 the indices g 2, 2, then delta 2, 2, and the determinant of g mu nu. So 2 means the zeroth coordinate is time. The first coordinate here is spherical coordinates is r, and the second is theta. And here we had minus r squared in the metric tensor, or in the determinant if we consider it here. So this is cancelled out, and so we have only 3 lines in 3 rows, and 3 columns here. And the determinant of the metric tensor, that is, we have 3 factors with a minus, so here a minus remains, and we have r squared and another r squared here with a sinus squared, and so the whole determinant of the metric tensor is this, what we have here in 118 in the denominator. And if we calculate in the numerator the determinant, that is only r squared sine squared theta, and that means we have a minus, and we have 2 r factors more in the denominator, so minus r minus 1 divided by r squared, and we see that is correct. This is a G22 element of the metric tensor. Okay, then we can also write the cofactor is equal to the differential quotient of the determinant G differentiated with respect to the G mu component of the metric tensor, the covariant metric tensor. So again, the example with the indices 2 and 2. So we have in the numerator that this is the determinant. So we have the 4 diagonal elements here in the product. And here we have G22 in the denominator. And yeah, of course, if we execute the differentiation, then the derivative is only the product of the 3 remaining elements here. And G22 is cancelled out. And yeah, if we multiply these elements, then we get r squared sine theta squared. And yeah, that should be the cofactor delta 22. And we can compare that here in 118. Here we have the explicit determinant in the numerator here. And the determinant is only the product of the diagonal elements. So minus and minus is plus. And we have r squared and sine theta squared. And see, yeah, that is the same what we have here in 119. Now we finish lecture 3. In lecture 4 we will look at calculations with tensors. Thank you for watching. See you next time. Goodbye.